Graphitic corrosion damage mechanisms as a part of uniform or localized loss of thickness. Description of graphitic corrosion based on API 571, Number A. Cast irons are comprised of graphite particles embedded in an iron matrix. Graphitic corrosion is a form of dealloying in which the iron matrix is corroded, leaving corrosion products and porous graphite. Number B. Attack results in a porous structure with a loss of strength, ductility, and density. It usually occurs under low pH and stagnant conditions, especially in contact with soils or waters high in sulfates. Graphitic corrosion damage. Description. Graphitic corrosion is a specific type of corrosion that primarily affects cast iron materials, particularly those that contain graphite as a key component of their microstructure. This phenomenon can lead to significant deterioration of the material's mechanical properties and structural integrity. Here is a brief definition of graphitic corrosion, its causes, environmental factors, effects, detection and prevention/mitigation. Number 1 is definition and mechanism. Graphitic corrosion involves the selective leaching or removal of the iron matrix surrounding the graphite flakes or nodules within cast iron. In aqueous environments, the corrosion process can selectively attack the iron, leaving behind the relatively inert graphite. As a result, the cast iron can develop surface irregularities and structural voids, which undermines its strength and mechanical performance. Number 2 is graphitic corrosion causes. Electrochemical processes. Graphitic corrosion is influenced by electrochemical reactions occurring on the surface of cast iron. The presence of moisture, dissolved salts, and acidic or alkaline conditions can accelerate these reactions. Restoration conditions. Environments rich in moisture or chemical contaminants, such as in wastewater treatment plants or coastal areas, can promote graphitic corrosion. Insufficient protective coatings. Lack of effective protective coatings or surface treatments increases vulnerability to corrosion, especially in aggressive environments. Number 3 is graphitic corrosion environmental factors. Chemical exposure. The presence of industrial chemicals, acids, or chlorides in the environment can exacerbate the conditions for graphitic corrosion. Temperature. Increased temperature may accelerate the corrosion process by enhancing the reactivity of the corrosive agents. Oxygen availability. Areas with poor circulation may create stagnant conditions that further promote localized corrosion. Number 4 is graphitic corrosion effects. Material degradation. As iron is leached away, the overall structure of the cast iron weakens, leading to reduced load-bearing capacity and increased susceptibility to fractures or failures. Surface morphology changes. The material develops a rough, pitted appearance as the iron matrix is dissolved, leaving behind aggregates of graphite. Loss of mechanical properties. With the matrix degraded, the tensile strength and ductility of the cast iron can significantly diminish, making it less suitable for structural applications. Number 5 is graphitic corrosion detection. Detecting graphitic corrosion typically involves visual inspections and non-destructive testing methods such as visual inspection, observation of surface pitting, cracks, and changes in the texture of the cast iron. Ultrasonic testing or UT. This technique can help identify changes in thickness and the presence of subsurface defects. Eddy current testing, used for assessing surface or near-surface degradation. Number 6 is graphitic corrosion prevention and mitigation. To prevent graphitic corrosion, the following strategies can be implemented. Use of protective coatings. Applying corrosion-resistant coatings can provide a barrier against moisture and aggressive chemicals. Material selection. Opt for corrosion-resistant alloys or treated cast irons designed to withstand specific environments. Cathodic protection. Implementing sacrificial anodes or impressed current systems can help reduce the electrochemical potential that drives corrosion. Regular maintenance. Conducting routine inspections to identify early signs of corrosion and addressing them promptly through repairs or protective measures. In conclusion, graphitic corrosion poses a significant risk to cast iron components, particularly in aggressive environments, leading to material loss and reduced mechanical performance. Understanding its mechanisms, causes, and effects allows for the implementation of effective prevention strategies, thus enhancing the durability and safety of structures made from cast iron. Regular inspections and maintenance are essential to detect this type of corrosion early and mitigate its impact on structural integrity. Graphitic corrosion affected materials based on API 571, primarily gray cast iron, but also nodular and malleable cast irons experience graphitic corrosion. However, nodular and malleable cast irons tend to crumble when attacked. White iron is not subject to this damage because there is no free graphite. Graphitic corrosion primarily affects certain types of cast iron due to their specific microstructure that includes a matrix of iron surrounding graphite. Here's a detailed overview of the materials affected by graphitic corrosion. Number 1 is cast iron. Gray cast iron, this is the most susceptible to graphitic corrosion. It contains flake graphite, which can become exposed when the iron matrix is corroded. The loss of the iron matrix can lead to significant degradation of the material. Ductile, or nodular, cast iron, while it is more resistant to certain types of corrosion compared to gray cast iron, ductile cast iron can still experience graphitic corrosion under the right conditions. The presence of nodular graphite shapes the material's response to corrosion differently. White cast iron, although it is less prone to graphitic corrosion due to its different microstructure, which has a higher percentage of cementite rather than graphite, if exposed to sufficiently aggressive environments, it may still experience some level of degradation. Number 2 is cast iron alloys. Various alloyed cast irons that contain elements such as nickel or chromium may develop graphitic corrosion in adverse conditions, particularly if they contain significant amounts of flake graphite. Number 3 is wrought iron. While wrought iron is less common today than cast iron, older structures made of wrought iron can potentially exhibit graphitic corrosion if they have been alloyed or treated in a way that encourages graphite formation. Number 4 is certain steel alloys. Some steels that have been alloyed in a way that encourages localized graphite formation, or that have significant cast iron components, may also be susceptible, although this is less common. Additional considerations. Environmental influence. The risk of graphitic corrosion increases in aggressive environments, such as those exposed to water, acids, chlorides, and other corrosive agents. Thus, even materials that are not typically prone to graphitic corrosion may become affected under specific conditions. Location-specific variables. Structures that are in constant contact with water, like pipes, tanks, or components in wastewater treatment facilities, are particularly vulnerable to this type of corrosion. In summary, while the primary material affected by graphitic corrosion is cast iron, especially gray cast iron, certain cast iron alloys and, in rarer cases, specific conditions in wrought iron and steel can also lead to similar types of degradation. Identifying materials that are susceptible to this phenomenon is crucial for implementing effective prevention and maintenance strategies in industrial and structural applications. Graphitic corrosion critical factors based on API 571, Number A. Graphitic corrosion occurs with several different cast iron alloys but is usually limited to very specific microstructure environment combinations. Factors that influence graphitic corrosion include the composition of the alloy and exposure conditions including temperature, degree of aeration, pH and exposure time. Number B. Damage occurs in the presence of moisture or an aqueous phase, usually below 200 degrees Fahrenheit or 93 degrees Celsius. Number C. Damage may take many months or years to progress but can increase in severity if the pH drops. Much of the damage occurs during stagnant conditions when high concentrations of sulfates are present. Number D. Graphite is cathodic to the iron matrix. The iron matrix preferentially corrodes and cathodically protects the graphite in certain conductive waters or soils. Number E. Graphitic corrosion may affect adjacent components by causing galvanic corrosion. Graphitic corrosion is a specific type of corrosion that primarily occurs in cast iron materials, particularly gray cast iron, due to the selective leaching of the iron matrix surrounding graphite. Several critical factors influence the development and severity of graphitic corrosion. Understanding these factors can help in preventing and mitigating damage. Here are the graphitic corrosion key critical factors. Number 1 is environmental conditions. Moisture availability. The presence of water is a primary catalyst for graphitic corrosion. Environments that are consistently humid or where cast iron is submerged in water are at higher risk. Chemical composition of the environment. Exposure to aggressive chemicals, such as acids, chlorides, or saltwater, can accelerate the corrosion process. These chemicals can enhance the electrochemical reactions that cause graphitic corrosion. pH levels. Acidic or alkaline conditions can significantly impact the corrosion rate. Extreme pH levels can lead to more aggressive deterioration of the iron matrix. Oxygen concentration. Oxygen availability influences electrochemical reactions. Well-aerated environments can exacerbate corrosion rates, while low oxygen levels might reduce the severity. Number 2 is material composition. Microstructure of cast iron. The amount and form of graphite, flake versus nodular, in cast iron affect its susceptibility to graphitic corrosion. Gray cast iron is most vulnerable due to its flake structure, which allows for localized corrosion. Alloying elements. The presence of alloying elements such as nickel, chromium, or molybdenum can enhance the corrosion resistance of cast iron but may also influence its susceptibility to graphitic corrosion depending on the environment. Number 3 is mechanical stress. Stress concentrations, areas of high stress or fatigue, combined with the presence of corrosion, can lead to accelerated degradation. Stress can cause microcracks in the material, creating pathways for moisture and corrosive agents. Load-bearing conditions. Structures that experience dynamic loading or impact may be more susceptible to graphitic corrosion due to repeated stress cycles that can exacerbate material degradation. Number 4 is surface condition. Surface coatings. The absence of protective coatings can increase vulnerability. Conversely, protective coatings can significantly reduce the risk of graphitic corrosion by keeping corrosive elements away from the surface of the cast iron. Surface roughness and cleanliness. Rough or contaminated surfaces can trap moisture and contaminants, encouraging localized corrosion. Smooth, clean surfaces are less prone to such issues. Number 5 is temperature. Operating temperature. Elevated temperatures can accelerate the chemical reactions involved in corrosion, leading to increased rates of graphitic corrosion. However, extreme temperatures can also change material properties, affecting susceptibility. Thermal cycling. Fluctuations in temperature can cause expansion and contraction of the material, potentially leading to the development of cracks and crevices where corrosive agents can accumulate. Number 6 is time of exposure. Duration of exposure to corrosive environments. Prolonged exposure to corrosive environments increases the likelihood and severity of graphitic corrosion. The longer the material is exposed to moisture and corrosive agents, the greater the potential for damage. Number 7 is design and geometry. Drainage and design features. Designs that trap water or do not allow for effective drainage can promote prolonged exposure to moisture, increasing the risk of graphitic corrosion. Complex shapes. Components with complex shapes may contain hidden crevices where moisture can accumulate, exacerbating the problem. In conclusion, the critical factors of graphitic corrosion encompass environmental conditions, material composition, mechanical stresses, surface conditions, temperature, duration of exposure, and design features. By understanding and addressing these factors, engineers and maintenance professionals can better prevent and manage graphitic corrosion in cast iron components, thereby extending their service life and ensuring structural integrity. Regular inspections, surface treatments, and material selection can significantly mitigate the risks associated with this type of corrosion. Graphitic corrosion affected units or equipment based on API 571. Graphitic corrosion can occur in soft water, salt water, mine waters, dilute acids, and in underground piping as well as in boiler feedwater equipment. Typical examples include feedwater piping, pumps, including pump impellers, valves, and underground cast iron pipe. Fire water systems are particularly vulnerable. Graphitic corrosion primarily affects cast iron components and systems, particularly those used in environments where they are exposed to moisture and corrosive agents. The following are some common units and types of equipment that can be susceptible to graphitic corrosion damage. Number 1 is pipelines and piping systems. Water distribution pipes, cast iron pipes used for transporting water, especially in older systems, are common targets for graphitic corrosion due to constant exposure to moisture. Wastewater pipelines, pipes conveying wastewater or sewage can also be prone to this type of corrosion, particularly in areas with high levels of organic acids and other corrosive substances. Number 2 is storage tanks. Water storage tanks, tanks made of cast iron for water storage are vulnerable, especially if not properly coated or maintained. Chemical storage tanks, tanks that house chemicals, especially if they are acidic or otherwise corrosive, can lead to graphitic corrosion in cast iron materials. Number 3 is valves and fittings. Cast iron valves, used in many industrial and municipal applications, these can develop graphitic corrosion, especially if they are not regularly maintained or exposed to harsh environments. Pipe fittings, associated with piping systems, fittings made from cast iron can suffer from localized corrosion. Number 4 is cooling towers. Cooling systems, cast iron components within cooling towers or cooling systems can experience graphitic corrosion due to constant water flow and chemical treatment processes. Number 5 is heat exchangers. Cast iron heat exchangers, these can degrade over time due to exposure to water and heat, particularly if they are not adequately protected or maintained. Number 6 is railings and structural elements. Bridges and overpasses, older infrastructure made from cast iron may exhibit graphitic corrosion, particularly in areas where moisture and contaminants accumulate. Railings and other architectural features, cast iron railings and features can be affected, especially those exposed to the elements. Number 7 is pumps. Cast iron pumps, used for various applications, including water and wastewater systems. If not properly maintained, they can be vulnerable to graphitic corrosion. Number 8 is sewage and drainage systems. Sewers, cast iron sewer pipes are particularly susceptible to graphitic corrosion due to their constant exposure to water, sewage, and corrosive substances. Number 9 is municipal equipment. Hydrants, fire hydrants made from cast iron can experience corrosion over time, leading to potential functional failures. Valve boxes, structures made from or containing cast iron components can develop graphitic corrosion. Number 10 is industrial equipment. Boilers, cast iron boilers may be vulnerable if the water chemistry is not properly controlled. Pressure vessels, some pressure vessels made from cast iron can experience localized corrosion if exposed to corrosive environments. In summary, graphitic corrosion can affect a wide range of units and equipment primarily made from cast iron. These include pipelines, storage tanks, valves, cooling towers, heat exchangers, structural elements, pumps, sewage systems, municipal equipment, and industrial installations. The widespread use of cast iron in various applications makes it essential to understand the risks of graphitic corrosion and implement appropriate protective measures, including regular inspections, maintenance, appearance or morphology of graphitic corrosion damage based on API 571. Number A, damage may be widespread or it may also occur in localized areas in which the majority of the component is unaffected. Number B, the damage may not be noticeable upon visual inspection even where the full wall thickness is degraded. Number C, damaged areas will be soft and easily gouged with a knife or hand tool. Number D, metallographic examination may be required to confirm the extent of damage. See Figure 4-103, graphitic corrosion of cast iron impeller due to glycol acidification. See Figure 4-104, cutaway of cast iron impeller shown above. The dark phase around the outside perimeter, at arrows, is graphite which surround the unaffected metal in the middle. See Figure 4-105, view of the outside of an underground concrete-lined saltwater service line that failed from graphitic corrosion. See Figure 4-106, view of concrete lining inside the failed line shown in Figure 105. See Figure 4-107, cross-section of a gray cast iron drainpipe showing charcoal-colored through-wall graphitic corrosion encroaching from both sides. Note the through-wall crack at the bottom. See Figure 4-108, cross-section of a gray cast iron pipe with graphitic corrosion coming from OD, point B. See Figure 4-109, higher magnification view of unaffected area A shown in Figure 4-108. See Figure 4-110, higher magnification view of the damage from shown in 4-108, area B. Graphitic corrosion typically manifests as distinctive morphological features on cast iron surfaces. Understanding the appearance of the damage can help in identifying its occurrence and assessing the extent of corrosion. Here are the key characteristics and morphological features associated with graphitic corrosion. Number 1 is surface pitting. Localized pits. The most prominent feature of graphitic corrosion is the formation of small pits on the surface of the cast iron. These pits are often irregularly shaped and vary in depth and diameter, depending on the severity of the corrosion. Conical or bowl-shaped. Pits may appear conical or bowl-shaped and can penetrate into the iron matrix. Number 2 is graphite peaking. Exposed graphite. As the iron matrix corrodes away, the embedded graphite flakes become exposed. This can give a speckled or mottled appearance on the surface where the gray graphite is visible. Dark streaks or patches. Areas where graphite has become exposed may appear darker than the surrounding metal due to the visual contrast between the gray cast iron and the black graphite. Number 3 is discoloration. Rust formation. In the presence of moisture, rust, iron oxide, may form in conjunction with graphitic corrosion. This iron rust can make the area look flaky, orange-brown, or red, depending on the extent of oxidation. Corrosion products. Other discolorations due to corrosion products, like tannins or salts, can also occur, affecting the overall appearance. Number 4 is texture changes. Rough or pitted texture. The surface may feel rough and uneven as the iron matrix deteriorates unevenly, leading to a change in texture. Deterioration around graphite during leaching. With time, the surface may develop a very rough and uneven landscape as the iron continues to corrode and the areas surrounding graphite flakes deteriorate. Number 5 is flaking and spalling. Surface flaking. In advanced stages, portions of the surface may flake or spall away, revealing the underlying layers of cast iron or exposing more graphite. Fragmentation. The loss of material can lead to larger fragments breaking off, compromising the structural integrity of the component. Number 6 is cracks and microcracking. Formation of cracks. In some cases, microcracks may appear in conjunction with graphitic corrosion, especially if there have been stress combinations, mechanical and environmental, affecting the material. Cracking pattern. The cracking may follow the grain structure or appear randomly, depending on the mechanical and thermal history of the component. Number 7 is layering. Pitting with layered graphite exposure. In some circumstances, multiple layers of corrosion may be present, with different areas exhibiting varying degrees of pit depth and graphite exposure. In conclusion, the appearance of graphitic corrosion damage on cast iron is characterized by localized pitting, exposed graphite, discoloration, changes in surface texture, and potential flaking or cracking. These morphological features can serve as key indicators for identifying graphitic corrosion in various applications, emphasizing the necessity for regular inspection and maintenance to mitigate the effects of this type of corrosion. Understanding these signs can assist in timely interventions and can help ensure the longevity and safety of cast iron structures and components. Graphitic corrosion prevention and mitigation method based on API 571, Number A. It is often difficult to predict if exposure conditions will cause this form of dealloying in a particular environment or service. One must be aware of the potential susceptibility of cast irons. Number B. Internal graphitic corrosion can be prevented by coatings and/or cement linings. Number C. External graphitic corrosion can be prevented by external coatings or cathodic protection in severely corrosive soils. Preventing or mitigating graphitic corrosion damage in cast iron components requires a combination of proper material selection, protective measures, and regular maintenance practices. Here are several graphitic corrosion damage prevention and mitigation strategies that can be employed. Number 1 is material selection. Use of alloyed cast iron. When designing components for environments prone to corrosion, consider using alloyed cast iron that includes elements like nickel or chrome, which can enhance corrosion resistance. Substitute materials. In severely corrosive environments, consider replacing cast iron with alternative materials such as ductile iron, stainless steel, or high-performance polymers that offer better resistance to corrosion. Number 2 is protective coatings. Surface coatings. Applying protective coatings, such as epoxy paints, galvanization, or powder coatings, can create a barrier that prevents moisture and corrosive agents from contacting the cast iron. Sacrificial anodes. In some applications, using sacrificial anodes can provide cathodic protection to cast iron components, helping to prevent corrosion. Number 3 is corrosion inhibitors. Chemical inhibitors. Incorporating corrosion inhibitors into the water or fluid systems can help reduce the rate of corrosion by forming protective films on the surface of the cast iron. Number 4 is control of environmental conditions. Moisture control. Ensure proper drainage and minimize water accumulation around cast iron components to reduce exposure to moisture. pH control. In aqueous environments, maintaining a neutral pH level can help minimize corrosion risk. Monitoring and controlling the chemical balance in water systems can be beneficial. Number 5 is design practices. Avoid traps for moisture. When designing components, consider shapes and configurations that avoid moisture traps and promote drainage. Minimize galvanic corrosion potential. When combining different metals, choose compatible materials and use insulating methods to prevent galvanic corrosion. Number 6 is regular inspection and maintenance. Routine inspections. Conduct regular inspections of cast iron components to identify early signs of corrosion. Visual inspections can help detect pitting, discoloration, and surface irregularities. Scheduled maintenance. Implement a maintenance schedule that includes cleaning, repainting, and addressing any identified issues promptly. Non-destructive testing. Utilize non-destructive testing methods, such as ultrasonic testing or radiography, to identify subsurface corrosion or structural issues. Number 7 is environmental modifications. Control exposure to aggressive agents. In industrial applications, control exposure to corrosive chemicals, acids, or salts that can accelerate corrosion. Use of water treatment. If applicable, treat water used in processes or systems that come into contact with cast iron to remove corrosive agents and control pH levels. Number 8 is installation practices. Proper installation. Ensure that cast iron components are installed correctly to prevent stress concentrations and errors that can lead to corrosion. Seal joints. Seal all joints with appropriate gaskets or sealants to prevent leaks and moisture intrusion. In conclusion, by implementing these prevention and mitigation strategies, stakeholders can significantly reduce the risk of graphitic corrosion in cast iron components and prolong their service life. A proactive approach that includes careful material selection, environmental control, regular maintenance, and protective treatments can help ensure the integrity and functionality of cast iron systems. Graphitic corrosion inspection and monitoring based on API 571, Number A, UT is not a good method for detecting damage. Number B, acoustic techniques, loss of metallic ring, and ultrasonic attenuation are applicable. Number C, a significant reduction in hardness may accompany dealloying, although affected areas may be localized. Detecting graphitic corrosion damage in cast iron components is crucial for maintaining their structural integrity and performance. Various inspection and monitoring methods can be employed to identify early signs of corrosion, assess the extent of damage, and implement timely maintenance. Here are some effective methods to detect graphitic corrosion damage. Number 1 is visual inspection. Routine visual checks. Regular visual inspections can help identify surface pits, discoloration, rust formation, and other signs of corrosion. Inspectors should look for flaking, exposed graphite, or any irregularities in the surface texture. Use of magnifying tools. utilizing magnifying glasses or borescopes can aid in observing small pits or other microscopic signs of damage. Number 2 is surface profiling. Profilometers. These instruments can measure the roughness of a surface quantitatively, helping to indicate areas of corrosion by comparing roughness measurements to established baseline data. 3D laser scanning. Advanced techniques like 3D laser scanning can provide detailed surface maps to assess areas of corrosion and wear accurately. Number 3 is ultrasonic testing or UT. Thickness gauging. Ultrasonic thickness gauges can be used to measure the wall thickness of cast iron components, detecting areas where material loss has occurred due to corrosion. Flaw detection. Ultrasonic testing can also be employed to detect subsurface defects or discontinuities caused by corrosion. Number 4 is magnetic particle testing or MT. Surface and near-surface flaws detection. This method can detect surface and near-surface discontinuities by applying a magnetic field to the material and using ferrous particles to locate cracks or pits associated with corrosion. Number 5 is dye penetrant testing or PT. Surface crack detection. Dye penetrant testing can reveal surface breaking defects that may result from graphitic corrosion. It involves applying a dye to the surface and observing where it seeps into cracks or pits. Number 6 is eddy current testing. Conductivity changes. Eddy current testing can be used to detect changes in material properties due to corrosion. It is particularly effective for thin-walled structures where traditional methods may not be applicable. Number 7 is non-destructive testing or NDT scanners. Automated NDT scanning. Use of advanced scanners that incorporate various NDT techniques can help detect corrosion in real time and allow for comprehensive monitoring of large areas. Number 8 is infrared thermography. Heat signature analysis. This technique can identify localized corrosion areas by observing temperature differences that result from corrosion-induced heat retention or conductivity changes. Number 9 is corrosion monitoring sensors. Electrochemical sensors. These devices can monitor corrosion rates in real time and are often integrated into systems where cast iron components operate. They measure parameters like pH, conductivity, and corrosion potential. Wireless monitoring systems. Advanced systems can provide continuous data on the condition of cast iron components, alerting to changes in corrosion rates. Number 10 is periodic wall thickness measurement. Long-term monitoring. Establishing a baseline wall thickness through periodic measurements allows for tracking material loss over time, which can be indicative of ongoing graphitic corrosion. Number 11 is visual data comparisons. Benchmarking historical data. Comparing current inspection data with historical records can highlight trends and help determine whether corrosion is accelerating. In conclusion, combining these inspection and monitoring methods allows for a comprehensive approach to detecting and assessing graphitic corrosion in cast iron components. Implementing a regular inspection schedule and using appropriate technologies can help in identifying potential issues early, facilitating timely maintenance and ensuring long-term structural integrity. Thank you.